All right, guys, we're back with integration part 2. Today we're going to focus on trig function integration. So we have a few more rules that we're going to need to go over. So let's go ahead and take a look at our notes here. So first rule, it's rule number 6 in the integrations series. We have the integral of cosine x dx is sine x plus c, which makes sense because if you go back the other way, the derivative of sine is cosine. So the integral of cosine is sine. Right? And don't forget, we need the constant of integration for all of these, s plus c, because the derivative of a constant would be 0. If we're going the opposite way, we need to take into account that that constant might be there. Number 7, the integral of sine x dx is negative cosine x plus c. Number 8, the integral of secant squared is tangent. Number 9, the integral of secant x tangent x is secant x plus c. Number 10, the integral of cosecant squared dx is negative cotangent x plus c. And number 11, the integral of cosecant x cotangent x dx is negative cosecant x plus c. So let's go ahead and look at some examples. Now, before we actually look at the examples, I want to stress to you the importance of kind of go through the 4-step process. We talked about this 4-step process with derivatives, and I think it's just as important to talk about it again with integrals. We referred to it as ORIS with derivatives. It just stands for original, rewrite, integrate, and then simplify, right? So a little different with the wording for this because of the integration, but it's going to be take the original and see if you can rewrite it. Rewrite it to make the integral easier or at least doable before you start. After you rewrite it, take the integral. And then after you take the integral, go ahead and go through and simplify. So the book suggests that you make a chart. I don't care if you make a chart or if you just go through the process. I'll show you one of mine towards the end in the 4-step process. And make sure you think about that. A lot of times rewriting it not only makes it more doable, but definitely makes it easier to complete the problem. Don't go straight to integration. So we're going to go through 3 examples, and then I will do one of the book problems just to show you the process that I went through. So hopefully that helps. I'll go ahead and share my screen here. Let me get plugged in. And make sure you write those integration rules down on a note card or in your notes. That way you have them as we go through. So the first example you're going to see is going to be a simple trig function. Let me get my cover-ups here. So the first one looks like the integral of 2 sine x dx, right? So before I start, I am going to try to rewrite this, right? Because I have a coefficient there of 2, a constant 2 I can pull out. So before I take the integral, I'm going to take that 2 outside and make it 2 times the integral of sine x dx. One of my rules was for the integral of sine x dx, so now I can go ahead and integrate. So the integral of sine, we saw in our rules, was negative cosine. So multiply that constant down through. So 2 negative cosine x plus c. Don't forget your plus c. Right? And then just to simplify it to make it look a little bit nicer, I'm going to multiply that negative times the 2 in front, make it negative 2 cosine x plus c. So really not that bad. Start off with an easy one. If we come over here, we look at example number 8 from your notes. It's the integral of 5 cosine x plus 4 sine x dx. Now, because we have several pieces, we're going to separate them out. And both of them have these coefficients, the 5 and the 4 in front, which we can also pull out of the integrals. So I did that all in the same step. I separated the cosine x and sine x into 2 separate integrals, and I pulled the 5 and the 4 out of each. Right? We do have an integration rule for cosine, and we have one for sine. So now we rewrote it. We can go ahead and integrate it. So when we integrate, we're going to get the integral of cosine is sine. The integral of sine is negative cosine. So I have 5 times sine x plus 4 times negative cosine x plus our constant c. And then I'm going to simplify it. Just make it 5 sine x minus 4 cosine x plus c. Right? And then our third and final example, this one is by far the hardest, right? You have to really think about the rewriting portion of this before you start, because we don't have a rule that allows us to do any sort of quotient, and we don't have a cosine squared. So you definitely have to rewrite this one first. So why don't you take a second and try this one out before we continue. All right, so now that you've tried it, your first step, you should be thinking, okay, well, so my first thought was taking cosine squared. I could use the Pythagorean identity, change it to something in terms of sine, but then I would still have a fraction, right? I would still have that fraction issue that I have right now. So that wouldn't help me. So then I went back to the drawing board and thought, what else could I do to make these look like some of my trig integration rules? So I thought, well, cosine squared I can pull apart. I can make it sine over cosine times 1 over cosine, because if I multiply them back together, I still get sine over cosine squared. So I didn't change the value of the actual original problem. After that, I know that with my quotient identity, sine over cosine is tangent, and 1 over cosine is secant. So I can rewrite that. So now instead of the integral of sine over cosine squared, it's the integral of tangent x plus secant x dx. Now, I don't technically have a rule for tangent secant, but the order of multiplication doesn't matter. So just so you could match it up, I switched it around. It's going to be the integral of secant x tangent x dx, right? You didn't have to do that last step because tangent secant is the same as secant tangent. But just to match it up, I think it will be easier to see if I change it to secant tangent. So now that I have something that looks like my integration rule, I can go ahead and integrate it. The integral of secant tangent is just secant, so secant x plus my constant c, right? Don't be discouraged if the first time you try to rewrite it, you don't get something that is worthwhile, right? Sometimes, like I said, if I would have changed that to 1 minus sine squared instead of cosine squared, that wouldn't have worked, at least for the rules that we have. So sometimes you have to go with the second or third option before you can get it down to use the rules that you have. All right, so now I'm going to do number 26, and we're going to practice this Forest method, right? So this is what the book suggests. This is the full process, right? You break it into some sort of chart or some sort of organization where you write the original, you rewrite it, which may take several steps, as you saw in some of these. You integrate it, and then you simplify. And you won't always have to rewrite it, and you won't always have to simplify, but it's good to think of them for each problem. So in this one, we have the original, the integral of secant y times the quantity of tangent y minus secant y dy. I don't have a rule with a product in it, so I'm just going to distribute that secant y on the outside through, multiply it through. So if I do that, I'm going to rewrite it to secant tangent minus secant squared, and the dy comes along. Now, if you notice in your trig function integration rules, you do have a secant tangent and you do have a secant squared, so we can stop the rewriting process there and go ahead and integrate it. The integral of secant tangent is just secant, so secant y tangent y would go to secant y. And the integral of secant squared y is tangent y, so I would have secant y minus tangent y plus c. Now for this one, there's not a whole lot you can do to rewrite it, so I just put my capital F of x equals secant y minus tangent y plus c. There would be some argument. You could make it like 1 over cosine minus sine over cosine, make it 1 minus sine over cosine plus c. But I don't think that does you a whole lot of good unless you're trying to solve or do something of that nature. So for us, we're just going to keep the actual integration and the simplified version the same. It's not always going to work out that way, but in this case, I think that's best to leave it like that. So that's number 26 of your homework. If you have any questions, feel free to comment below. Make sure you like and subscribe, and we'll be back for integration part 3 in the near future.